This is AS Module 2, the paper from June 05, question 3, and the topic is on lenses. The first question, define the principal focus of a diverging or concave lens. This is a very specific definition which I would suggest that you just learn rather than try to explain each time. It is defined as the point on the principal axis, and learn how to spell principal, from which all rays parallel to the principal axis appear to diverge from. So it's the point on the principal axis from which all rays parallel to the principal axis appear to diverge. Take the note that it's not just parallel rays, it's rays parallel to the principal axis is the main point within that definition. So it's the point on the principal axis from which all rays parallel to the principal axis appear to diverge. And you could say after passing through the lens there if you wish. The next part of the question then asks us to define the focal length of a diverging lens. This is the distance between the principal focus, which we've already defined, and the optical centre of the lens. You should refer to the optical centre in your definition. It's not just the distance between the principal focus and the lens, it's the distance between the principal focus and the optical centre of the lens. You need to be specific at A level. Part B then. A photographic slide has a width of 35.0 millimetres. An image of the slide is projected onto a screen. The width of the image of the slide is 1.4 metres and the lens of the projector is 6 metres away from the screen. So we've got quite a lot of information in there. Part 1, state the type of lens used by the projector. Well, a projector projects an image onto a screen. So if the image can be captured by a screen, it is a real image. Therefore, it must be a converging lens. Even though it's magnifying, it must be converging. A diverging lens will always give us a virtual image which cannot be captured in a screen. Therefore, for a projector, it must be converging. To calculate the linear magnification of this projector, well, we know two equations for magnification. We know that m equals v over u, where v is the image distance and u is the object distance. And we also know that we can calculate magnification by doing a calculation involving the image height and the object height, or size. So if I have a look at the information we've got, it'll help us to select which equation to use. An image of the slide is projected onto the screen. The width of the image is 1.4 metres. The slide initially has a width of 35.0 millimetres, and we know the distance of 6 metres from the screen, so that's the image distance. So we don't know the object distance, so we'll use the equation m equals image size divided by object size, and write out that equation. There's 2 marks there for it, so there's a mark for writing that equation or substituting correctly into it. The image size is 1.40 metres. The object size, looking back again, is 35 millimetres, so that's 35 by 10 to the minus 3 metres. That gets you the first mark, then doing the calculation correctly to get 40 gives you the second mark. Take care there that you convert from the millimetres to metres. If you don't, you'll get an answer of 0.04. And if you think about it logically, when you have a photographic slide, what you see on the screen you're expecting to be much bigger, not smaller. Therefore, you know your answer's wrong. So we must convert into metres. Calculate the focal length of the lens of this projector. Well, we need to use the lens law for that. And we know that 1 over f equals 1 over u plus 1 over v. We know what v is, we don't know what u is, we don't know what f is. Therefore, we're going to have to use some of our information from the previous question. We know that m is v over u. We know m, we know v, and we want to find u. So u is equal to v over m. The image distance is 6, the magnification is 40, so that gives us an object distance of 0.15. Then substitute that into the lens law. With 1 over f equals 1 over 0.15 plus 1 over 6. When you rearrange and recalculate that, you've got f equals 0.146 metres. So we used the magnification to find the object distance and then substituted that into the lens law. Then part 4. Describe fully the nature of the image produced by this projector. Well, it can be captured on the screen, therefore it's real. We've already seen that the magnification is 40, so the image is much bigger, so it's magnified. And because it's a converging lens, and that magnification, to have a real image which is magnified using a converging lens, it must be inverted. So to summarise that question again, we had to define the principal focus of a diverging lens and then the focal length. And then we selected the type of lens for a projector, bearing in mind it had a real image, therefore it was converging. A diverging lens always gives a virtual image which cannot be captured on a screen. So in this application it's a converging lens. We were able then to calculate the magnification of the projector using the image size over object size equation, and then substitute that in to the v over u equation to find u, then use the lens law to find the focal length of the lens. And finally we described the nature of the image produced, and because it's a projector with a real image and it's magnified, it must be inverted.